afternoon. My name is Orhan, my colleague Adrian Jerich, who will be introduced shortly. We're both on the ME6121 module for vehicle design and technologies, and this is our automotive networking assignment. We're specifically going to be talking about the CAN bus. CAN, short for Controller Area Network, is nowadays a robust vehicle standard for basically devices within your vehicle to communicate with each other. They're used in modern day vehicles, trucks, buses, the whole lot, as well as in the automation and medical instrumentation industry. Nowadays, cars have up to 70 different subsystems, for example, the power management unit, safety system, and the infotainment system. And if you think about it, you can't have wires going individually from each subsystem to your main controller. So where the CAN bus steps in is you basically have output from one single source, and rather than signals going individually from subsystem to subsystem, the signals go to all different subsystems, and whichever is necessary is picked up by the relevant unit. So by doing this, you have a cost advantage and a much cleaner wiring, as you're going to save on copper, and there's going to be a lot less interference between the signals. Just basically allows for a much tidier wiring system. So that's where it saves on costs. Other advantages include the fact that the camera system is very robust towards failures and interference. It's a very flexible system which can be easily modified by adapting the code to have however the user requires it, which we're going to talk about in a few moments. Another important thing is that the CAN bus very efficiently prioritizes the most important messages to the least important. So high priority messages being, for example, the feedback from the power unit or the information on the infotainment system. So this is a simplified CAN message with extended 29 bits identifier called CAN 2.013. So we have our starter frame, which basically tells other ECUs that the message is coming. Then we have our CAN message identifier, which, like I previously said, prioritize messages according to number. So something coded 00 would hold priority over something coded 01, for example. Moving on, we have our RTR, which is remote transmission request, which allows ECUs to request messages from other ECUs. Our control informs the length of the data in bytes. After that, we have our actual data, which needs to be scaled or converted to be readable and to be ready to be analyzed. After that, we have our CRC, which is used to ensure data integrity. After that, we have our acknowledgement, which ensures that the CRC process is in order. And after that, to conclude the CAN message, we have our end of frame. Important thing to know is our CAN signal, they're usually represented like that, with voltage from 1.5 to 3.5. The message is usually mirrored with the high voltage having being the dominant part of the message, identified as a 0 rather than 1, which is the inactive part of the message. Most outputs work electronically in 3 ways. We have a switch signal, which goes from on and off. We have pulse width modulated, which allows a device such as a motor to be operated at variable speeds by charging the amount of time electrical power is supplied to the device. That looks more like narrow signals or wider ones. Finally, we have communications, which is digital signals, mostly used for computer communications. Um, these involve voltage signals that are transmitted and received in packets. They have the same square waveform, with binary pieces of information.
Hello, my name is Adrian. Today we're going to be showing you the automotive testing rig of Mark 6 Golf CAN bus systems. So we put the ignition on. I'm just going to show you around. So, for example, you can put your lights on, brake lights, wiper motor shown just right there, hazard warning lights, the whole lighting system lot. We have been given a fault and we will be trying to solve it. So if I turn the car on and the lights on, I can straight away see there is on an MFD, and it shows a light bulb with an exclamation mark on it. So that indicates that somewhere there is a light bulb off, and also on the main screen it says the light brake bulb is not working basically. So we do a visual check. It's clearly there's clearly shown that the bulb is not working. So if I look at the diagram and locate the wiring of the that module of this brake light unit, clearly shows the I have to put a pin on M21, which stands for module 21. So once we located the control module for this brake light unit, we're going to turn on the voltmeter to 20 volts direct current and test the module. Black pin into the ground and red pin into module 21. The voltmeter shows me that there is no voltage on module 21, so therefore there has to be an open circuit somewhere in the system. So for the open circuit, the other test we can do is the continuity check. So if I switch the multimeter to continuity check, if I put once again black wire to the ground and red wire to module 21 of the brake light system, and there is no beeping sound. And if I go to the back of the module and test the LED system is actually working, I put a wire into a black and the pin into the black and white system there, and into the pin here you can see the beeping sound. So therefore this module of LED system is working, so there is something wrong with the wiring. The CAN bus light unit tests the circuit with 3 energy pulses. So the unit found there is a fault in the circuit and put up the message on the MFD. Now let's say I presumably fixed the wire on this testing rig, and let's test it if it works. But visually you can already tell it's already working, but let's check it, just make sure with the multimeter it works properly. So once again with 20 volts direct current, it shows me there is 3 volts, and if I press the brake pedal, there is 12 volts. Again with the continuity check, if I press the brake pedal, you can hear the sound. Over here we've got Pecan View software, which decrypts the data from CAN bus system and puts it in a readable way for the human being to read. Over here we've got CAN ID, which is an identifier, the type of it, the length of the code, also known as control, the data, which in this case we just tested the brake light system. So if I switch the brake light, the code changes over here, and the cycle time, which is the circles per minute, like counts per minute.